interested in next is we had PV equals RT, so that enables us to do pressure, temperature, and specific volume. But what about the energy terms of internal energy and enthalpy? How can we deal with that? And that's what we want to look at next. So we have specific heat at constant volume. And so it's defined as, C sub B is defined as the change of internal energy with respect to temperature at constant specific volume, and the units are kilojoules per kilogram degree K. What this implies, so mathematically what this implies, is that U is a function of temperature and specific volume, so I can write the total differential, du is equal to du dt at constant V dt plus du dV at constant T dV. And so what we're interested in, so this is what this is, and it's like, my goodness, what's going to happen? So we have an experiment was done that is eventually going to show that U is equal to U of T only for an ideal gas. And let me tell you about what that experiment was. It was done by Jules, who seemed to do a lot of experiments. And so this is what it was and how he evaluated it. So again, there's a sketch in the text that looks a little nicer than mine, but mine's intriguing. So anyway, we have a water bath, and we're going to have two spheres. They were spheres connected to each other. So I have a sphere here, and there's a line. We have a valve. The handle could go up. We don't want anyone to get their hand wet. 1 and 2. So the spheres 1 and 2 comprise our system. P1 is high, so it has a high pressure in it, and P2 is near 0. So it's a vacuum. They evacuated one, they had a high pressure in the other, and they let thermal equilibrium exist. So now we have T equals C, thermal equilibrium. And they put a thermometer in here. And so what they did, so they let thermal equilibrium exist, so the temperature of the water was the same, everything was at the same temperature, and then they opened the valve. They didn't get their fingers wet. They opened the valve, and the mass in here went in here, so the specific volume changed and the temperature was constant, and if there was any heat flow, so if we look at Q is equal to delta U plus W, the volume was constant. If there was a change of internal energy, then there would have been heat flow in or out of the water, and there would have been a change of temperature. Nothing happened. That meant delta U was 0, or that U was not a function of specific volume for an ideal gas. So no change in T, and therefore we have that U is equal to U of T for ideal gas. And I can say that C sub B is equal to du dt, so I can write it as a total derivative, or du is equal to C sub B dt. And if I integrate this, so I can integrate this, and I have U2 minus U1 is equal to C sub B times T2 minus T1. And obviously I could have large U2 minus large U1 is equal to M C sub B T2 minus T1. And where do you find C sub B? In that magical table A1. So I can look that up in table A1. And so I can find that, And because it's a property, it's true for all processes, and we'll go through that again, but this is a property. I have this expression for internal energy right here. Let me rewrite it. du is equal to c sub b dt for all processes. Reversible, irreversible, whatever. C sub b is determined experimentally under certain conditions, but once I have that value, I can use it all the time. And we also want to create a value for enthalpy, and if I look at C sub p, so we have the specific heat at constant pressure, and so we have that C sub p is defined as dH dt at constant P. And again, what we want to do now is look at an ideal gas. And so we have H is equal to U plus PV. Its definition for an ideal gas H is equal to the internal energy is only a function of temperature, and PV equals RT. So the enthalpy of an ideal gas is only a function of temperature. So H is equal to H of T for ideal gas. And thus I have that C sub P is dH dt, or dH is equal to C sub P dt. Again, we find that in table A1. So we're looking to find that in table A1. I can integrate this, and I get H2 minus H1 is C sub P times T2 minus T1, and large H minus 2 minus large H1 is M C sub P T2 minus T1. So now we have three equations of state that replace all the steam tables, which is why I did chapter 4 first, because if I did this first, you would say, why do I have to learn this if I have the ideal gas law? And the answer is, this doesn't work for liquids and vapors. And so I have PV equals RT. I have dH is equal to C sub P dt, and du is equal to C sub B dt. And I have these three equations of state. And I'm able to replace tables of property with these three equations of state. And now there's a couple more little things to look at in terms of some terms that we use. And one is K, we use the symbol K, is C sub P over C sub B. Some books in physics, you might use gamma, but I'm not going to write it down. They sometimes use gamma. And now let's go back and we can express, let's investigate this enthalpy term. So I have H is equal to U plus PV is equal to U plus RT. dH is equal to du plus RDT. And then I have C sub P dt is equal to C sub B dt plus RDT. And the dt's cancel. And I end up with R is equal to C sub P minus C sub B. So I have an equation for R in terms of specific heat. And I also have that R is equal to R bar divided by the molecular weight. So I have these three functions. And now what I want to do is that gases, actually the specific heat varies with temperature, and I wanted to look at that. So if I look at figure 510, it'll give the variation of C sub P with temperature. And it'll be something like this. And for helium, we have something like this. And this is for different gases. And what happens is the way energy is stored in the gas molecule changes with time. What happens for helium is that it can only move in 3 directions, so its value matches very easily. But let's go in and just qualitatively talk about the kinetic theory model about energy storage in a gas. And this goes back to chapter 2 when we looked at the modes of energy storage for internal energy. So for the kinetic theory, model, we're looking at degrees of freedom F of molecule motion. Now for helium, it can move in the XYZ direction, so it can go this way, or back and forth. And so we have 3 degrees, so F is equal to 3, and it has to do with the XYZ motion. And we saw that translational kinetic energy relates to temperature. So as the temperature goes up, everything remains constant. So I have a constant value here because we're not introducing other modes of energy storage. If I look at a more complex gas molecule, and so let's look at hydrogen. So look at a diatomic molecule. So if I look at a diatomic molecule, we'll see there's 3 translational modes. So that's the XYZ. There are 2 rotational modes. And I had talked to you about the rotational modes for a diatomic molecule. They could rotate around, each atom could rotate around its center of mass, and we could have the whole thing rotate. And we have 2 vibrational modes. And so we have these modes, so we have F is equal to 7. So F is equal to 7, and what happens is, and if we plot this on the C sub P versus temperature diagram, which is in the text, and it's a log temperature function. So if I have 50 degrees K, 400, 3000. So here's T, C sub P. And basically, it's constant up until here. Then we have an increase. So this was A, B, C. And what happens at different temperature, different modes kick in. So in the beginning, I'll only have translational modes. Then as the temperature increases, I have translational plus rotational. Energy making it rotate doesn't correspond to an increase in temperature. Only the translational modes increase temperature. So we have this variation over the temperature range. And what we typically do in engineering problems is we pick an average value of C sub P over the temperature range that we're using. So in practice, we pick, let's say, C sub P Av over temperature range. And what that does is assume a linear variation of C sub P within that temperature range. And now what I'd like to do is start looking at some problems.